In this lesson, we will learn something about electron control devices, which will include, for example, vacuum tubes, semiconductors, diodes, transistors, and logic gates, to name a few. It is not all-inclusive of everything we need to know on the subject. Additional information can be found in the General Aviation Maintenance Technician's Handbook and in Acceptable Methods, Techniques, and Practices of Aircraft Inspection and Repair. Vacuum tubes were technological marvels in their day, but have since been largely replaced by solid-state devices. As electrons absorb heat energy, they become excited, and once enough energy has been absorbed to overcome the forces binding them to an atom or molecule, they will break free. And once free, they leave behind positively charged ions. There is then a force of attraction between the unlike positive ions and free of electrons, keeping the electrons from escaping the environment. This results in a cloud of electrons surrounding the cathode. There are four general types of vacuum tubes. Diodes are used to rectify alternating current, and triodes to amplify a voltage drop. Tetrodes and pentodes are both also used as amplifiers. Vacuum tubes have largely been replaced by solid-state devices because they are smaller, cheaper, more rugged, and require less power. The size and weight advantages of solid-state devices can be observed here with the vacuum tube seen on the left in this picture and the solid-state device performing the same function on the right. Semiconductor diodes are used to rectify alternating current into direct current. The symbol for a diode can be seen on the right. The arrow points to the negative side of the circuit. A forward bias diode will allow electrons to flow from the N material to the P material. A reverse biased diode stops the flow of electrons in the external circuit. A diode can be tested with an ohm meter. A rectifier is used to convert alternating current into direct current. Diodes are used to accomplish this because they allow current to pass through them in only one direction. In one-half wave rectification, only one-half of the electrical power input gets transferred. A full-wave rectifier utilizes two diodes to convert the entire alternating current waveform to direct current. A half-wave rectifier allows electrons to flow only during the half cycle when the cathode is negative. A full-wave rectifier utilizes two diodes to change both halves of the alternating current into direct current, increasing efficiency and producing a smoother output. Bridge-type rectifiers use four diodes to eliminate the need for a transformer to produce the desired output voltage as required in a full-wave rectifier, thus increasing efficiency. On the top left of this page, we see the input signal as an alternating current waveform as it would be upon entering the bridge-type rectifier, whose circuit is pictured top center. It consists of an alternating current power source, 4 diodes, and a resistor. Because this serves as a full-wave rectifier, we can see on the top right that the full alternating current has been converted to direct current. Because diodes only allow currents to pass in one direction, we can see from the circuit diagrams C and D on the bottom of this page that regardless of the polarity of the incoming AC waveform, the current always passes through the resistor, or sub L, in the same direction. We have already learned that we need 2 diodes for full-wave rectification. A 3-phase rectifier would then logically require 6 diodes. Here we can see the 6 diodes needed for 3-phase full-wave rectification in an automobile alternator. The diagram on the top of this page depicts a single-phase unrectified waveform whose voltage goes from a peak value and back to 0 every half cycle. The diagram on the bottom depicts a 3-phase unrectified waveform generated every 120 degrees, whose voltage goes to peak but never drops to 0. On the bottom of this page, we see a fully rectified 3-phase waveform whose voltage only drops slightly from peak, creating a much smoother output. Xanier diodes can serve as voltage regulators. Transistors can be used to amplify current and can be used as a switch much like a relay. We can use a small current at the base to control a larger current at the collector emitter. Like transistors, relays can be used as a remote switch and utilize a small current to control a larger current. Running a heavy gauge wire capable of carrying the power necessary to operate an aircraft starter, along with a heavy-duty switch capable of handling that current, takes up already limited space on the panel. It also increases the likelihood of an in-cockpit fire, as well as increased interference with radios and navigation equipment. A relay allows us to control that heavy current flow from a remote location, reducing these problems. Relays and transistors each have their own advantages and disadvantages. There are 2 main types of transistors, the PNP and the NPN. Like diodes, transistors can also be tested with an ohm meter. Unlike other transistors, a field effect transistor controls current by controlling voltage. Magnetic amplifiers allow us to control larger currents than do vacuum tubes and semiconductor devices. Photodiodes use light to control current flow. Phototransistors are more sensitive to light than photodiodes. There are several devices which smooth the pulses of rectified DC. Logic gates are digitally controlled binary circuits. They take one or more logic level inputs to produce one logic level output. Make sure you take the time to memorize the symbols for the logic gates following. An AND gate requires a certain input at both terminals A and B to get the desired output. This is analogous to the circuit below with two switches connected in series. Both switches must be closed for the bulb to light up. An OR gate requires a certain input at A or B to get the desired output. In the circuit below, we can close either the top or bottom switch to get the bulb to light up. In a NAND gate, a certain output is achieved except when a particular input occurs at both A and B. A NOR gate obtains a certain output only when there has been no input at A or B. In an exclusive OR gate, a certain output is achieved only with a particular input at A or B, but not with both.